Okay, so we started with a very simple model. Everything has the same value, constant biclusters. Each row and column in the submatrix needs to have the same value. Then we generalize that by allowing some kind of variation along rows or columns, but still we said we need constant values in either rows or in columns. Now, the next step, obviously, for generalization is to allow variation in both directions, in both rows and columns, and that brings us to the next model, which is biclusters with coherent values, and that's what we are looking at now. So the cluster model basically looks very similar to the ones above, as I said before, but we now have so to say two adjustment values. We still have this specific value, constant value mu here, as we had in the very beginning, and then we had these adjustment values for rows or columns, and now we have adjustment values for rows and columns. So that is the cluster model of biclusters with coherent values, coherent over rows and columns, so to say. Well, obviously our models from above, from before, constant rows, constant columns, are special cases of this cluster model, because constant rows means that we have a zero adjustment in the rows, and a constant column, a zero adjustment in the columns, of course, then we have constant rows. And if we have constant columns, is the special case where we have an adjustment in the rows, which is zero. So Ri is 0 for all the rows, then we have constant columns, and if Cj is 0 for all the columns, then we have constant rows, obviously. Okay, just compare that with the previous things here. Okay, so that is the basic cluster model. The question is, what is the spatial pattern that we get? So that is the matrix pattern. We see that here, down here. So constant rows and columns here. So we have the same adjustment from the basic mu here in all rows and columns. So maybe that's the most easiest way to look at. We have mu 0. So we have 0 as the basic value here for mu, and then we see, okay, we have, for the first one we have 1, 2, and for the second one we have 2, 3, 4, 5. So the adjustment overall is always the same, so to say. So that is the basic pattern in the matrix. And the spatial interpretation is that the points build a hyperplane which is again parallel to the axis of the irrelevant attributes. So just as before with the constant row values, we have the same, more or less the same pattern in general, that we have points that are on located on a hyperplane, and the hyperplane has an arbitrary shape, arbitrary spread along the irrelevant attributes, which is in that case A3. So it's parallel to A3. So A3, because A3 is the irrelevant attribute here. So once again, the spatial interpretation is, if we project the whole thing down on the relevant attributes, it's again now some line here. The points form a line in the relevant subspace, an increasing line, or even, if we sort them correspondingly. But now, different to this one here, which is the bisecting line here, always on the bisecting line here, the points need not to be, or the line that is formed by the points need not to be the bisecting line anymore, because we also have the adjustments according to the columns, not only to the rows. So that is the generalization here of the two above patterns, actually. And the visualization of, or the pattern, the parallel coordinate visualization is that we have, again, as before here, parallel lines, but they need not to be constant anymore. Yeah, so it's a combination of this pattern here and this pattern, obviously. Yeah, so this here is the bisecting line, is a line on the bisecting line actually. Yeah, and this one here in the constant columns is somewhere, but not necessarily on the bisecting line. And we have here these identical lines that may change, and here in the constant rows we have parallel constant lines, and the combination now is, well, spatially these hyperplanes, these lines that need not to be on the bisecting line, and here parallel lines here again that need not to be identical anymore. Yeah? So parallel lines in the relevant attributes A1 and A2, and of course again an arbitrary spread along or in the attributes which are irrelevant, which are not part of the sub matrix here. Yeah? So those are the biclusters with coherent values, and that is the most general part so far. If it comes down to values or identical values, or at least similar values, once again in all of those models, of course we could introduce a kind of similarity threshold where we say, okay, we don't necessarily assume or require the model to be exactly this model. Yeah, so the equality here could be something like approximately, with a kind of similarity threshold. So we can also say that the values should be approximately following this model here, and if they are close to this model here, or closer to this model here than a given similarity threshold or a given error threshold, then we say, okay, the corresponding values are still in this cluster here. Yeah, so we may allow here 1.1 and 2. Or 1.9 or something like that. Yeah, instead of an exact match of this cluster model. Yeah, and we could do that in all of the other models, of course. And that is the most general one if it comes down to these similar or even identical values. Yeah, because the next thing is a little bit more about evolution of or change of the values in the submatrix. Yeah. Okay, so that was biclusters with coherent values, and as I just said, the next one will be a little bit different, because now we allow also changes in an arbitrary quantity, but the direction of the change needs to be the same, and that will be biclusters with coherent evolutions, meaning that the change need to be in the same direction. The evolution of the points of the values need to be in the same direction. Yeah, and that's coming up.